personal request. We're going to finish up with weathering and then talk about the cross-section, the famous cross-section problem that's been creating so much heartache and anxiety and high stress amongst some of you. And I guess that's what it's supposed to do, so that's probably okay. Nothing wrong with a little bit of anxiety and stress. It makes you operate at a higher level of efficiency. So we're going to finish up weathering here, which shouldn't take too long. And then we're going to talk about the cross-section and then what the homework's going to be. And then we're going to move on into Chapter 5, which is soil mechanics. So we were talking about travertine last time and salts. And I can't remember exactly where we got to. Did we talk about erosion by water and wind yet?
That's where we started. Where we are.
We were actually in the middle of that when we stopped?
I think so. Somewhere in the middle.
We started
Number 7.
limiting values of runoff.
Slide number 7, limiting values of runoff. This one here?
Yeah.
Okay. Sorry, I can't remember. It's a while back. So this chart is a chart that we I'm going to get over here so you can see the stuff that we use all the time in the profession. It's a Corps of Engineers publication. And there's two things I want you to see here. One is there's clear water numbers right here, which don't exist in, those are only in civil engineering laboratories where they have distilled water flowing through flumes. So that's a nice theoretical number. And then right here is the one that's silty water. Now when you have a storm and you go out there and watch the flow, which is highly instructive, you're always going to see turbid water. You're going to see, generally, you're going to see silty water, especially if you get out west of the 100th meridian, where we have a lot of erosion. So the Missouri River Basin only has 25% of the runoff that is contributed to the Mississippi River, but it has over 75% of the sediment load. So it's the muddy Missouri, no question about that. The Ohio River's got a lot more water, but nowhere near as much sediment because it's coming from a humid area where you have lots and lots of plants and trees anchoring everything down. The Missouri, upper Missouri River, once you get over to middle of Dakota and in middle of the Dakotas on to the west is all desert. And so that's where you're going to get lots and lots and lots of erosion. And so that's where the big sediment load is. Now a lot of that sediment is caught in Fort Peck Dam, Lake, and a lot of it's caught in Oahe, Garrison, and Fort Randall lakes. So we don't have anywhere near as much sediment coming down that system and feeding to the Mississippi as we had prior to 1960. And as a consequence, in part due to that, in large part due to that, we're losing about 35 square miles of land mass in the delta, down in the Mississippi Delta today, as that land consolidates and settles under the ocean. Now we also have sea level coming up over the last 100 years. It's been coming up over the last 15,000 years, but the rate has slowed and it's about 12 inches a century now. So if we have global warming, it may be even a little more than 12 inches, maybe as much as 18 inches over this coming century. So we have that complicating factor as well with all this land disappearing. Now why this is important as practicing engineers is when you go up here and try to protect something by putting in riprap or gravel or something like that, you got to realize that velocity is your enemy, and velocity is going to tend to build up on a slope, such as on a dike. And so about 2/3 of the way down a 300-foot long dike, you're going to reach some critical traction velocity. We're going to start cutting the root mass, and once you get those roots off, maybe they're just inch deep, half-inch deep, fescue grass isn't very deep rooting. Once you break that root mat, whew, you're off to the races. And what you have to have here is clay. So if you come over here and you look at these different materials, sand doesn't have a lot of resistance to erosion. It doesn't have any cohesion. It's a frictional material, nice clean beach sand, about 33-degree phi angle of internal friction, no cohesion. Sandy loam can be, it's going to have a higher apparent cohesion and a higher apparent friction, and as long as it doesn't get saturated, it can do quite well. Once it gets to saturation and gets disturbed, it disappears. Silty loam, non-colloidal, alluvial things. As you go down here, the thing that really resists is stiff clay. And you see stiff clay, we go across, and you're looking at 5 meters a second that can withstand, 5 feet per second. And you can get up to 6 feet per second with some materials like coarse gravel. Above 6 feet per second, things are going to start disappearing. And what this doesn't show is stream power. Stream power is the Q you're looking at, the quantity of flow and the duration. So the longer you have it moving there, the more things are going to start to move, transmit kinetic energy from one particle to another, and things are going to start coming unglued. Now when they start coming unglued, then you get roughness. You have places where it gets very, very rough, and you're going to get negative pore pressures and stuff pocking out, and the erosion, once you get to that point, it goes very, very rapidly. When we have a landslide dam across a major river, and these are our biggest floods that we have in the world, are landslide dams. They don't occur real often in the continental United States, but they're a very common occurrence in the Hindu Kush and down in the Andes in South America. When these things fail, no matter how big they are, some of them are almost a mile high, they disappear in 12 hours. So all that material gets eroded out in 12 hours, and by 24 hours, your hydrograph is down to where it's going to be for the next few hundred years. That's how fast it erodes. So landslide dams are the big thing that's not on most people's radar horizon, and they create much larger floods downstream than conventional floods. So if we go out in the western Grand Canyon today, we look at some of the work the USGS has done there over the last decade, we have catastrophic outbreak floods from the failure of landslide dams and lava dams that are over 2,000 feet deep. These are things that are 5, 6, 7 times the height of Hoover Dam that went blasting down that canyon and left these terraces, and they use optical stimulated luminescence techniques to date those kinds of events. So those are the big events that are out there. If you go to work in the Hindu Kush or the Andes, you will see these terraces everywhere. They're not riverine terraces, they're landslide dam outbreak flood terraces. If we look at a typical raveling cut, this is a typical kind of consultation I would get in California. I have a southwest facing slope here. Southwest facing slope means hot in the afternoon. You can put things up here, you bring the Boy Scouts out, and you can plant little trees along here, and they'll cook like Thanksgiving turkeys over the next few months in the warmth of the afternoon. So this thing has no shade, and you have a lot of drying going on, and you have a little thin veneer up here of soil which is supporting these annual weeds, the grasses that are growing there. And the grasses don't have a whole lot of erosion resistance when you get on a cut slope that's 26 degrees, like this is a 2-to-1 slope. Now the reason nothing's growing on this slope is several-fold, and you want to put on your scientist eyes here. So put your engineer part of your brain away and let's play scientist. Now scientists love to study things. They especially love to get money to study things. And after they study it for a while, they ask for more money to do more studies, because that's what they do. Okay, so if we look at this slope, we can say, why is nothing growing on this slope? And that's what the client was saying to me, saying, I can't get nothing to grow on this slope, except a few oleanders. Right here, that's an oleander, just barely hanging in there. Well, for one thing, slope aspect. It's facing southwest, and southwest is the heat of the day. So you have an issue there with just heat and evapotranspiration loss. So if you're going to put anything up here, you're going to have water for it. Some kind of constant source, and there's got to be water there that's going to keep it from reaching wilting point, which is going to reach in a day or two pretty easily. 2, you have raveling going on. You have active raveling occurring. You can see this loose talus stuff right here, very actively raveling out of the desiccated zone coming off this clay residual cap up here, which is only about 1.5 feet thick, 16 inches. So you have active raveling, and that's hard to get something established on the slope when you have active raveling. And then you have soil chemistry, pedology, soil science. And this is a tertiary sediment. It's a Pliocene sediment that was in a volcanic basin with calc-alkali volcanics. And so what we have here, we have a situation where we have a very high alkaline soil, and it doesn't have a lot of the nutrients you would need to supply annuals like nitrogen. There just isn't any there, because they did a cut slope here. So trying to revegetate something like that isn't a matter of just putting down an Excelsior mat and spraying fescue on it and then sprinkling it with water. Wouldn't it be nice if it was that easy? Now, I got news for you. In Missouri, it's that easy because it's humid here. You feel like a poached fish around here in the middle of August. It's raining and it's very humid, and you can get grass to grow around here even if you don't try. It grows. Okay. Not that way in California. Nothing simple in California. That's why they have so many problems there. Things don't just grow on a slope like this, or they wouldn't be calling somebody like me. Now, this is a difficult consultation, and it's one that I frankly walked away from, because I gave him the little speech I just gave you and said, you know, I can spend a lot of time, energy, effort, and very good chance I'll come up empty. And by this time in my career, I'd been out there for 10 years. I was a little smarter than what I was when I started. And by that time, I realized if I don't give the client something that they want, they're not going to pay me. They're not going to want to pay you. They're going to stiff you. And that's one of the sad facts of life. You know, you try to avoid highly libelous work or work with clients who have unrealistic expectations. This client had wholly unrealistic expectations. They thought I could come out here, you know, spray paint it with green Rust-Oleum and just fix it all up for $30. You know, why should this cost very much? It's only grass, I mean, you know. And I said, well, you know, you need someone to tend it. Maybe what you should do here is plant marijuana and then have somebody, you know, tending the marijuana. And they would watch it very carefully. Here's a stepped cut in a Precambrian metamorphic rock complex along Interstate 210 between Sunland and La Cañada. And this cut is over 200 feet high. It was made back around 1969-70, so it's been there about 40 years now. And this is in Precambrian gneiss and schistose rocks. So these are rocks that are very, very difficult to get anything to grow on them theoretically. But you're in Southern California, near LA, where everything has been tectonized and sheared and lifted up out of the basement very, very rapidly. We're not far here from the San Gabriel-Cucamonga fault system, so this has been lifted up very, very rapidly, probably something around 6 to 13 millimeters a year, in that range. And so the state came in here and made stepped cuts, like they make in Arizona. Now, stepped cuts are where you go up 3 over 6, up 3 over 6, doing a 2-to-1 slope. This is a 1.5-to-1 slope, so they're going up, you know, 4.5 over 6, going up 4.5 over 6, and getting a 1.5-to-1 slope. Now, 1.5-to-1 slope is about 33 degrees, and they're stepping it because they're trying to break up the formation of erosional rivulets or gullies that would get down here and then accumulate little talus cones out onto the shoulder of the highway. So when you're doing highways, it's a whole different game. Highways and railroads, you have full-time maintenance organizations. If you're the Corps of Engineers, you have a full-time maintenance organization. You may not have funding to go out and do a lot of things you'd like to do until there's a disaster, but you have organizations that are responsible for maintaining it, so you don't have to design it, you know, so that it has a, you know, enormous amount of redundancy, so you never have to come out there and pay any attention to it again. Now, when you do subdivisions for wealthy people, that's how you have to build them. We have performance-based codes. We have performance-based expectations. People say, you should build it so that I don't have to go up there and feel threatened by this thing. Well, sometimes that's realistic or possible. A lot of times it's not possible to do that. So they came in here and they just made the stepped cuts, and they assumed that the cut would always be barren. Now, when you walk up here and you look at the slope close up, what do we see? We see all kinds of slaking and disintegration of this very hard basement Precambrian metamorphic rock. Look at this stuff breaking up. just spontaneously breaking up when exposed to unloading and air and LA smog. This thing is breaking up, and we have all kinds of volunteer things in here. Greasewood, creosote, and grease brush just growing in here all over the place. This is the stuff that burns and makes the real nice hot forest fires and nice charcoal, mesquite charcoal, And this was a total accident. And in the landscaping parlance, we call these volunteers. In other words, we didn't put them in there. They just blew in with the winds, planted themselves in the joints, because that's the only place you're going to get any water on a rock slope is in the joints. And voila, they've taken off, even on a southwest exposure, and have grown. Now, what if you're in an area that doesn't have any vegetation? This is Monument Valley, up near the Utah Arizona line, just inside Utah. And this area had about 40% more moisture annually during the Pleistocene, like Missouri had. So it was a lot wetter there. In fact, it had as much as 80% more moisture if we go a little further back in the Pleistocene. So if we go into Grand Canyon, I have a grad student who's been working down there on these old landslides, very old landslides, and we were looking at palynology. These are pollens that are left in the little lake deposits in the back of these large landslides. And when we look at those pollens, we find that in the Grand Canyon, we had Canadian blue spruce and ponderosa pines growing all the way down to the river's edge back during the Pleistocene. That was a much nicer tourist destination in those days in terms of the weather. Very different weather. We've had a progressive drying out there during the last 15,000 years, 16,000 years, just drier and drier, especially the last 7,000 years. So it's a virtual desert down below the rim. So we got these species that have, retreated up into Canada over the last couple 100,000 years. And so this is Monument Valley, and you can see here all these rivulets you see, right? These erosional rivulets are remnants of a wetter climate that doesn't exist anymore. And so what you have going on here is you have more detritus being produced by natural processes than there's stream power available to remove it. And in these kind of places, you really gotta be careful, because you're going to get big accumulations of colluvium and landslide debris, especially debris flow fans. You get large accumulations of that stuff in places that you wouldn't recognize today because everything is frozen in time right here. This is like, boom, somebody just turned it all off and said, okay, no more weathering. Well, it does weather maybe 6 days a year. They get enough rain to cause big problems right now. This area, when it really rains and they get flash flooding, it just wipes out roads. You go to a place like Death Valley. I remember working there, my first job out of college. We had Artist Palette Drive, and I was there in the summer of '76. And a couple months after I left, they had a big storm came in off the Gulf of California, the Sea of Cortez, hit that thing, and they had so much sediment come down there, they buried the entire fan in about 6 feet of alluvium. So they didn't dig the old highway out. That was ridiculous. The highway would be down in a hole. They just built a new highway on top of the new fan. One event, 1 year in the fall. Wow. That's what can happen to you when you're in a place like this. So you have to be careful of colluvial-filled bedrock depressions in places like that. Now you'll also see things like this, which are inselbergs. And most inselbergs like this, what they love, you love to use these in the Roadrunner movies, Mimi, going by. These are kind of inselbergs. They're usually controlled by joints. So you have regional systematic joints that usually form these nice, smooth faces you see here. And then you have the transverse set cutting off the other way. And you're also going to have secondary joints, which are more curvilinear, and they form in response to the free surfaces. Now, I got really interested in secondary joints as a grad student because that's what I learned to rock climb on at Yosemite National Park in Royal Robbins Mountaineering School. And that's how I got really interested in exfoliation joints and secondary joints, because as rock climbers, we depend upon those to put our climbing hardware into. And then I learned pretty quickly that if I put my climbing hardware in there in the afternoon, if I stopped too early in the day and jammed all my nuts and hexes and stuff in there, in the morning when it was about 30, 40 degrees cooler, I couldn't get any of that hardware out. And being a Scotsman, you know, I was really challenged, going, I got $100 worth of anchoring gear here. I can't get it out because the rock contracts with temperature, big time. Any rock climber knows that. So rocks do respond to temperature. Differential weathering is something you always want to be on the prowl for. You always want to be observing it as you drive by, as you go out on the freeway. If you have different stratigraphic units, you're going to have differential weathering generally. And differential weathering isn't just the lithology of the unit, it's the intensity of the jointing. Things that are brittle, like siltstone and shale, believe it or not, are intensely jointed. So they tend to erode more easily because you're divided up into smaller blocks. Doesn't take as much pore pressure to push those things off as it does a big block. So here you can see you have something here. This is a mushroom hoodoo. We got something that's ironstone cemented up in here. This is carbonate cemented down here. And so this is more resistant. This is one over in Owens Gorge in the Bishop Tuff. And this is just from the water going by on the Owens River. And the water is actually traveling in this direction. And this water, the high water line is, you know, this is low water, there's high water. And the water has a tremendous abrasion because of the silt load. Silt has as much abrasion as sandpaper. And so this tuff here, which is a relatively homogeneous volcanic ash, it's experienced differential erosion from the turbidity of the channel flow. And that makes good sense. Here I am standing next to a large block of Shinnerup conglomerate back in 1978 at Lee's Ferry, Arizona. And this big hunk of conglomerate, which came off that cliff way up there, that little cap rock, this is carbonate cemented, and it's a very good, nice boulder pebble conglomerate. And it fell on a pedestal here. The old surface that was right here was Moenkopi shale, which is a Triassic unit. And this Moenkopi shale is in tremendous compression. So you can see the little joints right here. Joint, 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 joint. But this has so much dead load on it right here that you have higher friction. And what actually happened here is there was a body of water here behind one of the lava dams 200 miles downstream. That lava dam suddenly broke, and all that water whooshed out of here, leaving these pedestal blocks there. So you want to be looking for stuff like that. Whenever you have catastrophic flood events, you're going to see things like these. And you're going to go, now wait a minute. How did those things get there? Are those part of an ancient Indian landfill? Are they part of some kind of, religious cult? How do those things get there? Well, you want to ask yourself those questions. Now, the nice thing is, be careful how many geologists you ask. Because if you ask 12 geologists and they're all drinking beers, you're going to get 12 different answers. And geologists love to argue about stuff. Engineers just want to say, hey, I asked you for an answer, give me an answer. And the geologist won't give you an answer. They'll argue about it. They'll go, well, it could be this, or it could be that, or it could be that. And the engineer always shakes his head and walks away and goes, they don't really know, do they? No, they don't know. They're guessing. That's we call that an educated guess. That's judgment. You charge more money by calling it judgment. You can't get any money from your client calling it guessing. All right, ventifacts. Ventifacts are one of the unique things that we have in desert areas that are very semi-arid and arid. You have a lot of wind blowing by. The wind's going to pick up the fine material, and off it goes into the atmosphere. And we didn't really realize in the old days how much stuff moved through the atmosphere until we got space-based platforms with Earth Resources Technology Satellite in 1973. And we started seeing things like the Barstow to Vegas motorcycle race was putting millions of tons of dust up into the atmosphere, and that dust was moving all the way across the continental United States. Now, when they first found out about this was in the 1920s when they were building the Empire State Building. And that was the highest building in the world by quite a bit at that time. And they had these steel workers way up there high in the building. And they started complaining about stuff hitting them. And it just got, after a while, it just get irritating. This little thing, and they thought they were bugs, but they couldn't find any bites. But it was starting to affect safety. And so it was the era of enlightenment, you know. What is this? What's going on? Let's go get a professor. So they went over to Columbia University, and they brought the professor out, and the professor said, well, we'll go up there, and we'll take samples of the air with these butterfly nets, these real thick canvas nets, and then we'll go back and look at what the nets catch in the microscope. And what did you think they found? Anybody want to hazard a guess? What did they find? I've told this story in GE50, so some of you should know who were in my GE50 class. Do you remember? It was the day you were sleeping. I know. Okay. It was wheat chaff from Kansas blowing along above 1,000 feet. So people are going out mowing down the wheat fields, and the chaff, you know, goes into the atmosphere and takes a long, long trip all the way out over the Atlantic Ocean. That's over 1,000 miles away. So a lot of stuff travels through the air. We're just not aware of it. And we're monitoring that kind of stuff today. It's amazing. So all this fine stuff gets blown away. We call this an ablation surface. And most of the desert floor that you see on these alluvial fans are debris flows. Debris flows are the dominant depositional process that we have in semi-arid and arid areas. So every once in a while, you get enough intensity and duration of rainfall that you mobilize material in a matrix that's very highly turbid, high density, can be 90 PCF instead of 62, which is what clear water is. And this stuff comes down like a wet concrete and just flows onto the fan. Now, if you go down Grand Canyon and you go down any of the side canyons, that's all you're going to see is debris flow deposits. Very easy to recognize. How, Uncle Dave? Matrix supported. It's always matrix supported. You will not see a boulder touching boulder like you would if it was water deposited. In water deposition, you have stratification. Because at a given Q, you have a certain size of material that'll all be the same size and imbricate laid down. So you know when it's water deposited versus debris flow deposit. We'll be talking more about that in debris flows in Chapter 6. But that's the dominant process that moves everything. So all the down cutting in the Grand Canyon is done in the steep side canyons. It isn't done by the Colorado River. Colorado River doesn't have steep enough a gradient to move those kinds of numbers of stuff unless it's fine grain. Colorado River moves silt and clay. But the cutting are landslides, and then the traveling down to the river is debris flows. And that's what you see all along the Colorado River, all the way back to its sources. Rocky Mountain National Park and in the Wind River Range in western Wyoming. Now, when this ablation surface blows off the fines, you actually get a settling of the debris flow materials, and the heavy stuff, like these big guys, settle out. And then these become venefacted. Venefact is something that's polished by dust and sand and silt carried by the wind. So ventifacting is very, very common, and that's why Bedouins aren't stupid enough to sleep on the ground. You know, they have these goat hair tents they make that are a good half-inch thick. And those things are so dense, you cannot blow talcum powder through them at 100 miles an hour. Because otherwise, their ears would get filled up at night. If a Bedouin does have to sleep out in the open and doesn't have his goat hair tent to get under, they'll sleep up off the ground about 18 inches. Because you don't get as much stuff in your ears in the morning. Because the stuff at night, the sand blows along, bumps into another one, blows along, bumps into another one, and that all occurs in a zone about 12 inches deep. So if you're going to sleep out in the desert and you have a lot of wind blowing, you know, get up on top of the Jeep and put your bedroll there. All right, here's some stripes that I photographed back in '73 at Lake Powell. And these are, this is Glen Canyon Dam right here, which was completed 1964 on the Colorado River. It's just a few feet lower than Hoover Dam, more concrete than Hoover Dam, and a lake that's second only to Hoover Dam. Lake Powell here has a capacity of 29 million acre feet. That's about 30 times the size of Lake of the Ozarks at high water. If Lake of the Ozarks was spilling at Bagnall, it'd be about 30 times that size. And what you see here are these big stripes going across the landscape. See those? Looks like some giant came along and went. Those are prevailing wind stripes from southwest to northeast. If we didn't have all the trees around here along the I-44 corridor, we'd see similar things around here. That's our perennial wind direction around here. About 2/3 of the time, we get Tulsa's weather. The weather comes up 44, right up the 44 margin, goes right here from southwest to northeast. So you want to be looking for things like this in the air photos, the satellite imagery, and it gives you an idea about the wind. All right. Wind is a real tough one to put a number on unless you can go out and find something in the literature out there. And the Soil Conservation Service usually has information in their literature about that, what their estimates are on it. Depends whether the ground's broken up or not. So what are some notes on constructing site cross-sections? How your cross-section looks is exceedingly important. It has to have good graphics. No one's going to believe you in this visual society with all the beautiful computer graphics unless it looks believable. And one way to make it look believable is to use the proper sorts of standard symbols that you see in field geology books. So if you have a copy of Leahy or any of the good field geology books, you want to use these kinds of symbols if you're dealing in a black and white world. Now, a lot of people now are doing things in Corel Draw and just doing them in color, and then they'll have a symbol thing over here, a legend saying, well, this color means this and that. And that's fine as long as everything's in color. But somebody is inevitably going to copy your product in black and white and give it to somebody, and then they're going to be lost. So I like to always use the symbols because I'm from the old school. Here's my first cross-section out of college. And I'm drilling a bunch of holes along Grizzly Peak Boulevard up above the city of Oakland, California. And it's an erosion problem where we had a culvert that had a big storm. And there was so much discharge going down this little culvert. I mean, it was like an 18-inch culvert or something. And it dug a hole 40 feet deep in this colluvium, in this material right here. 40 feet deep. That's a 4-story high building, much higher than Toomey Hall. One storm. Wow. Very, very angular material. The phi angle of this material, 45 degrees. 45 degrees won't help you if you have concentrated flow pouring on it for hour after hour after hour. That storm duration, by the way, was 35.5 hours. That's a long duration storm. Average storm duration, coastal California, 90 minutes, hour and a half. So to go 36 hours, that's a pretty unusual event. What happened there was they had a big banana express, we call them pineapple express, big, wet, warm storm, New Year's Day. It was actually a couple days after New Year's, January 3-5, 1982. And what happened is this storm came chugging into the coastal area and then hit a high pressure area over the Sacramento Valley. So the storm got stalled because it couldn't move across the high pressure area. So it just dumped all of its water and dumped and dumped and dumped it. And then more came in and dumped and more came in because the storm couldn't advance in its regular pattern. So I came in here and tried to, correlate boreholes. And, hey, how hard can that be? I went to grad school and did all the problems we had in grad school, and they were all incredibly simple. I never saw anything that simple ever in my career, like I saw in school. So we have two kinds of cross-sections. Make-believe ones that you see in school, and the real ones that you hate seeing when you get out in the real world. And here's a real-world one. What's going on between B4 and B9? This unit, which was a white material like I'd never seen before. It looked like pure kaolin. altered tuff. I think that's what it was. And we had a black altered chert here too. And this thing just, nice and thick. Picked it up here, picked it up there, diving off like that. And B9, gone. What happened between here and there? I don't know. Some kind of shear or something went through there. And I just brought it here and went dot, 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 dot. Now today I would have put a little question mark here or something. I know a lot of my colleagues, if they were going to publish this, they just wouldn't show B9. They just have this come on out and it would look nice and nobody would know that B9 didn't encounter that. Because you wouldn't get it past editorial review. Some pinhead at some university would say, "That's not possible. That's not possible. I've never seen that, so it's not possible." Oh, you haven't seen everything yet? Jeez. Well, these kind of things happen all the time. They happen all the time. Now, here's real world. Bedrock landslide, active slide right here. Previous slide, a lot smaller. This previous slide had been repaired with a buttress fill right down here. The original hillside, which had been graded less than 10 years previous, was right there. And after they had done this repair, a couple years later, lots and lots of moisture, and this thing comes out and mows down about 8 houses, all of which are around $750,000 value houses at the time. This is about 1994, 95. So we come out there with large diameter bucket auger rigs and start putting down bucket augers. Now what we're trying to do here is see what the structure is and see if we have more slide planes down below us. And here's the regional strike and dip of the tertiary sedimentary units. We never got into that. We were down 170 feet, never got into anything that hadn't moved. This is just one slide, 2, 3, 4, 5, 6. And when you drop in another hole closer to the other one, things only got more complicated because you have so much contortion of stuff getting moved around through this old land slippage, and you're looking at a three-dimensional situation here in 2 dimensions. You can never completely unravel it. You could spend your whole PhD on it, trying to unravel it, I suppose. But as engineers, all we need to know is enough to go fix the monster. We don't need to know everything about its birthright and the dates of recurrence and everything like that. So what you're trying to do here by going down these large diameter holes is take structural information. And you're recording that. Someone up on top of the ground is writing it down. You're doing the things, and you're taking samples of the slide planes so you can run shear tests on them, trying to back out the whole thing, get a picture of what's going on. It's exceedingly complex. It's much more complex than you were led to believe by anything you saw in school. So I just wanted to expose you to it and let you know. This is a case where a name brand firm came in here with soil engineers, and it's a slump. Don't need no geology to do a slump, and they were the low bidder. So they went out here and they drilled a few holes and they said, well, there's the slide plane. That's a pretty shallow failure. We'll just put this buttress in here. They had no concept that there were deeper slide planes down here beneath them. So they got sued, and they had to shell out 6-figure settlement on the thing. And scary. And that kind of stuff happens all the time. And those kind of... Now, we have your problem here. This is the problem I gave you. And this is what the Hungarian geologist did with this data. They had this data through a trench right along here, and they had these borings. And they had experience in the area, which you didn't have. They had experience, and so this is the picture that they drew. And in a minute, when we get out of the slides, I'll show you what the actual answer was. Okay. Now, most of the programs that are out there today, and they come by through my office all the time, there's all these programs you can buy that do the correlations automatically for you, because computers are smarter than people. We can program the computer to do everything. I haven't been able to convince my wife of that yet. She still wants me to do all sorts of things for her that can't get the computer to do. But anyway, the computer is going to make straight line correlations. And when you see those straight line correlations, 2 things. It wasn't one of my students, and it was done by computer, because there's no straight lines in geology, okay? So you're embarrassing yourself showing stuff like that. This is typical of what you get from a house full of soil engineers with no engineering geology in the roof. Now, that's great. What if this hole, Z7, wasn't there? What if we were just dealing without that hole? And you can see they show a fault right here. And they'd use this in their advertisement because they're trying to show you how sophisticated they are and how they can actually handle a fault. Blah, blah, blah. Isn't that interesting? Well, obviously, you would just show these things going straight on through. And you'd miss stuff like that. In reality, that's what happens all the time. You miss stuff like this because you didn't have as many holes as you might have had because you're the low bidder. That's how you get the job. So I remember when I first did work for Asian Development Bank, I was off in Taipei, Taiwan, which I know pretty well, and I'm looking at 5 borings for a bank building. Nice big high-rise bank building. 5 borings. I wasn't impressed. I said, 5, huh? Yeah, we, the geology, we know geology really well here. We don't have to, do 30 boring, or anything. So I'm looking at the borings, and I grew up in the business, and I'm looking there, and wow, these things really correlate well. In fact, this unit had the exact same thickness and the exact same moisture contents at every depth. 17.38% moisture, 17.39, I mean, to the second decimal place. You know what that is? That's BS. That's impossible. You can't get those kind of correlations. You give me a soil sample right here. You're going to see. I'm going to show you when we get into Chapter 5. I can't get that kind of reproducibility. Trying to get that kind of reproducibility. What they were doing there were 2 real borings and 3 dummied up borings. That's how they were the low bidder, and that's how they made money on the job. So they were missing things. And I ended up having to walk away from the consultation because I said, I'm not going to sign off on this. This person should be put in jail. Oh, you say that, in public, you're going to get slapped with a defamation suit. Fine, I'll be on China Airlines tomorrow. I'm out of here. And I did. The last job I did for Asian Development Bank. Every job I reviewed for those guys was like that. So I hope they're not watching this. All right. What are the 3 deadly sins of engineering geology and geotechnics? Number 1, never allow yourself to draw geologic cross-sections using a ruler. You can start with a ruler, but you don't finish with a ruler. Go get a French curve. Get a flexible curve. They have flexible curves over here. That's your friend. You're a geologist, you got a flexible curve. You're a structural engineer, you got a ruler. Okay? No such thing as ruler straight lines in geology. Always construct multiple cross-sections without vertical exaggeration. That's the problem I had with my geology employees. They were always doing things with vertical exaggeration so they could see all these depositional things. You go down here and work in New Orleans District Corps of Engineers, all their cross-sections are at 128 to 1. I don't know how they arrived on that, but that's what they use. 128 times vertical exaggeration. That's the only way you can see where the channels are, because everything's so darn flat down there. You could land a 747 anywhere, took the trees off. But if you're going to look at loading, like loading and reaction geometry, a passive wedge, an active wedge behind a bulkhead wall, you got to draw those things to scale, or you're going to screw up. I had some engineers once out of Stanford that actually did a slope stability stuff for me, and they used an exaggerated section, and they said, oh, don't worry, we just divided everything by 3. It doesn't work. If you had a 3-to-1 vertical exaggeration and you divide everything by 3, you're not seeing it like it really is. You need to draw the passive wedge, the log spiral shape of it, the Coulomb solution. You need to draw the active wedge to see where they are physically. This becomes of critical import when you start designing stuff next to channels and on hillsides. Because what you're going to find out real fast is you don't got the wedge out there you thought you had. You got water or air. And that's where you get into trouble. Guys that use charts that are assumed, they don't realize it. Those charts were developed for level front fill, level back fill. Then they apply it to a slope situation. They're going to get the wrong answer. Okay, so you're going to have to appreciate the apparent dip of the various units. Apparent dip is incredibly important. In geotechnics, we tend to look at everything with two-dimensional analyses, and we know that's wrong. You can't do that for complex wedges. Complex wedges in things like hazardous waste landfills, where you've got geomembrane liners. You've got to look at it from both the true dip direction and apparent dip directions. You've got to look at it every way you can. Whenever I look at landslides, block glide slides, we're going to see it I've never had one go straight down the dip. It's always at some angle to the true dip. So the true dip's this way, but they made the cut over here, so the thing fails that direction toward the cut. Come on. It's a no-brainer. But don't do the analysis just down the true dip. It's like looking at a seepage analysis on a levee. If you go into the core manual, on the office manual for levees, they always have the seepage cross-section 90 degrees to the levee. So all the water in the world is only supposed to seep under levees going perpendicular to the axis of the levee. Never does that. Ever. Ever. Go out and look at a map. Channels going like this, they build levees semi-parallel to the sinuosity of the channel. Those old channels are cutting under the levees at acute angles. And when you do the seepage analysis along the line of seepage, you're going to get a different answer. And that's a big problem that we have to get over in the 21st century. When you start analyzing them that way, I had them do this out in Sacramento, and 75% of the seepage analyses they did at the design height failed. Just doing it that way instead of the 90 degrees to the axis way, which dates back to the 1930s. Come on, kids, we've got to learn a few things since the 1930s. Follow the water. Okay, never allow yourself to average shear strength values when you get a low factor of safety. That happened down in New Orleans before Katrina. Slope failures are going to tend to occur along the weakest horizons. They're going to find, and sampling those horizons is always going to be difficult. So if you have a 1-inch layer of something that's really soft and gooey, that's what you got. And it's going to control behavior on that site. The reason you got the geologists in there on your team is to find that kind of stuff and to nail it down and figure out where it's going. And if it's going off in a different direction, that's great. It's not going to hurt you. But if it's going off in a direction where it can move, where it's not as well confined, it can kill you. Kill your company, kill your career, kill everything, kill everybody. So you want to appreciate the three-dimensionality, especially of old depositional pathways and channels. So that's Dave's 3 deadly sins of engineering, geology, and geotechnics. If you don't learn anything else out in this course, print this out and just know that. And then I will have accomplished a great deal. Because I didn't really take these things seriously when I began practicing. And I made a lot of mistakes the first 10 years of my career. There were things I didn't see that when I went back and revisited those jobs, years later, I'd look at it and go, oh my gosh, there's an old slide. I didn't see it with my double PhD from Berkeley. No, I didn't have experience. You got a double PhD doesn't mean, it means you wrote a lot. And you stayed at school a lot, and sweated a lot, and missed a lot of ball games. It doesn't mean you have engineering judgment. Engineering judgment comes from work under good people. So it's who mentors you that is crucial to your career. Don't look at what they're going to pay you, where they're going to send you, any of those other perks. What you want to ask is, who am I going to be working under? Who's going to mentor me? Is it going to be Felix the cat? Or is it going to be somebody who's really worthwhile? Because you're going to be influenced by whoever mentors you. All right, so let's go look at the answer now on the cross-section problem. Hopefully I have it here. I'm not seeing it. Oh, I thought I had it in here. I don't see it. All right. Well, so much for that one. Huh. Yeah, I didn't bring it. All right. Let's see if I have it on my thumb drive. Okay, we're going to close this. Oh, I forgot to bring it. Sorry. All right. Well, we'll move on. I'll bring it in next week, and we'll look at it at that time. Okay. You need to get in everything on Chapter 3 if you haven't gotten it in. And now we're going to make assignments. Our next chapter is Chapter 5, which is the chapter on soil mechanics. Instead of doing rock mechanics first, I do soils first, because that makes more sense to me. Soils are up on the ground surface. And then we'll do an overview of rock mechanics. Now, I'm not going to teach you everything about soil mechanics or everything about rock mechanics. All I'm going to teach you are the things that I didn't learn in school that I learned in practice, that are adjunct in addition to the basic stuff in the book. I want you to know the basic stuff in the book. I only assign like 5 chapters out of the whole book. You should read those chapters and answer the questions. Now in Chapter 5, get a pencil, because what we're going to be doing is these following questions I want you to do. We're not going to do all of them. I'm going to miss one of them. We're going to do 1, 2, 3, 4, 6, and 7. So that's in Chapter 5. So if you go back of Chapter 5, that's going to be, look it up for you here. That's going to be on pages 160 and 161. So 1, 2, 3, 4, 6, and 7. You're leaving out number 5. Now, a few notes about soil mechanics. If you look on, we also have a list of questions that are on Blackboard called Homework Questions, Soil Mechanics, Chapter 5. So let's see if we can go to the internet and dial up Blackboard. Oh, that wasn't what I wanted. Let's see, I think we can do it here. Where's the delete key? There it is. Oops. Wow. I thought that was a delete key, because it's not. There we go. Now it's going to look a little bit different for me because I'm a faculty, but I'm going to take you to the Blackboard site for the course, which is 341-1A, fall semester 2010, right here. All right. I want you to come over here to course documents. Now you should be copying all this stuff. This is a lot of useful stuff that I used in a lot of the forensic cases, a lot of the legal cases that I had out in Oregon, Washington, California, Nevada, and Hawaii. So if you look at these, there's limitation of liability clauses we're going to talk about when we start preparing reports and preparing simple proposals and reports, which will start next week. Schedule of charges and terms, that's just a typical, that's an old one now. Schedule of charges and terms. You always have to list that in your proposal. This thing here now, we're going to get into the things that are soil mechanics oriented, and this is a USCS, Unified Soil Classification System, which is what most people use in the country. ASTM uses it. There are other systems out there that are even better, but a lot of people are not trained to use them. But we're going to use Unified Soil Classification System. Also, we have a chart here that I got out of the old NAVFAC manual called volume, weight, density, porosity relationships. This is the chart you want to take to the PE exam with you. So you better have that one. I use that piece of paper more than any other piece of paper in my career. I refer to it more often than anything else because it has, you know, if I know the density, I know the specific gravity, how do I figure all these other things out? It's all there. So it's really a wonderful little chart to have. Then I have a little cheat sheet that I put together on soil plasticity and Atterberg limits, which helps you to do the unified soil classification system for silts and clays. And then I have a unified soil classification system flow chart. So how you troubleshoot and go through the flow of classifying a soil when you're in the field and when you're in the lab. Now in the field, you make guesses, and you have what's called a field log. That field log is always subject to change based on the laboratory classification tests, which are sieve tests and plasticity indices. And you throw away the field logs. You don't save those, because attorneys will use those to incinerate you on the stand. Because, you know, well, you called us a clay, Dr. Rogers, and over here you're calling it a silt. You know, it's obvious you don't know what it is, do you? It's obvious I'm going to kill you after this courtroom session. So you want to just get rid of that kind of stuff. You know, if it's a draft or it's a field log, it's subject to revision. You keep the final revision, you burn the other one, okay? You'll learn that when you get out in practice. Technical description of rock cores is stuff we're going to be doing later in the chapter on rock mechanics. And so these are the things you need for some of the assignments you're going to be doing here. Now let's go down and look at assignments, and it should have the chapter 5 questions there. So there's your homework question, chapter 3. And writing assignment number 1, which you should be starting on as well here soon. If I have time today, we'll go over what that is. And then the one I want you doing right here is homework questions, soil mechanics. These are just some extra questions. These are questions that I actually wrote for the national PE exam, so you might see them again. Hint, hint, hint. So they're just basic kind of stuff you should know how to do. I don't know why it's not coming up. There? I have to hit that?
No. Go ahead.
It's the yellow bar.
Right here? Oh, I don't know. Up here? This one?
Yes. No.
All right. Open. Sesame. Huh. So what am I waiting for now? Okay. There we go. So according to Unified Soil Classification System, you know, I'm going to give you some stuff there. And these are the kind they love to give on the PE exam. And what I want you to notice here is, notice 49%. Yeah, 49% is important, because everything that SCS depends on is if it's by weight more than 50%, then that's what it is. So 49 is as good as 1. It's what's over 50 that matters. So be careful. And then you got to know what the A line is. What is the A line? And that's actually covered in that plasticity handout that I just told you about. And then know what the term D10 means. 10% finer than, that size. That's a very important one to know. And then also realize that poorly sorted and well graded are the same thing. One's the parlance of geologists, the other one's the parlance of engineers. Now, if you're an engineering geologist, you're going to be using engineering descriptions. You're not going to be using geology stuff anymore. You've got to get a lot of that geology stuff out. You give them a geology thing, and you're going to confuse them. So you want to use engineering terms. So well graded means we have a lot of different sizes in it. We're not going to have any huge voids. We got little stuff to fill in, the little voids, and it packs down nice. And we have a well graded mixture when we put down aggregate base underneath pavement. I mean, it's so well graded that after you roll it, you can pour a canteen on it and you won't get anything going into it. That's how tight it is. Whereas poorly sorted would mean lots of the same thing. Lots of different materials. Because in geology, the only time you get poorly sorted material is in a debris flow. The rest of the time, it's always well sorted, all one size. And this is what's driven the Corps of Engineers nuts on doing levees all over the country. They'll come up with a specification that has a well-graded filter mixture and say, where do you get this filter material? Out here in the river. Rivers don't have well-graded material. Go out and look at them. What do they have usually? One dominant size. You want to make a well-graded mixture, you're going to have to work. W-O-R-K. You're going to have to take some stuff over here, take some stuff over there, take some stuff over here, and mix it together to get a well-graded mixture. And that fails to occur over and over and over because they use a canned spec done downtown in the big building, and none of those engineers likes to get dirt on your feet. So they don't actually go out and look and say, does this shit exist? No! It's not there. Yeah, it's what happened with the San Jacinto levee failure, California. Corps project had a 25% flood against it. It disappeared. 25% of the design flow. Did you miss the mark by a little bit? I'd say yeah. Someone missed the mark by a whole lot there. And the problem was that channel didn't have the material. It was spec'd. There was a standard specification in the contract document. It didn't exist out there. It was all real fine-grained granitic sand. All same size. Very fine, no cohesion. And they made a levee out of it. And they call them, the locals call them sugar levees. I say, why do you call them sugar levees? Does something sweet grow on them? No, when you put waters against them, they disappear like sugar in hot water. Wow. Hell of a dam, huh? It's like that stuff you give your kids, you know, you put it in the tub and it disappears. Okay, anyway. Well, that's, you know, you got to go out and look in the field and see if the spec's out there. A lot of time the spec's not out there, and usually the contractor will inform you of that. But sometimes the contractor doesn't inform you of that because it would cost them a whole lot more money to do something about it. And they just hope that it won't fail till they're safely out of state and have the money in Vegas. All right. So in soil mechanics, how is the term soil moisture content usually expressed? You need to know that. That's very important. And 3 basic components in a soil mixture: solids, gas, and water. And what is the inclusive term Atterberg limits? What does that mean? And Atterberg was a soil scientist in Sweden back in the early part of the last century. And so he didn't do this stuff for engineers. Engineers borrowed it because it was good stuff. Okay. Well, I think we can... Should we go back here? Is there anything else I want to show you? Oh, I have to go all the way back and start over? Oh, that says unavailable. Hang on. Let's see. There it is. Okay. And this is, by the way, the stuff I'm telling you about, it wasn't like there weren't people at the Corps of Engineers that know all this stuff. I'm not the only guy in the world that thinks about it. It's that you have to have somebody with that experience and judgment and savvy who's in the project management team. That's the key thing. You got to have somebody who's watching the QA/QC, quality assurance and quality control, and asking the tough questions. Saying, okay, this is a nice spec. We use this spec everywhere. Does that material exist out there? And at San Jacinto, it didn't exist. There was no way you could have met the gradation spec out there, and easily. It would have cost you a whole lot of money. It would have doubled the cost of the project almost. And that's why they didn't do it. And they got caught in that particular case. All right. Well, let's go on to... I'm going to talk about expansive soils first today because that never got covered real well when I was in school from a practitioner point of view. And where I learned the most valuable things about expansive soils, which are the most pervasive soil mechanics problem in the world, is expansive soils. The only thing that causes more real property damage in the world is dry rot. Dry rot is far and away the big one out there in terms of casualty loss. But expansive soils is far and away out there the biggest thing in the geotechnical world. And we have expansive soils right here in the Ozarks. in Raleigh. We have the oldest erosional surface in the country here. So what I'm going to do is just tell you some of the things that I want you to know that aren't in the book from a practitioner viewpoint. So here we are looking at a house that has moss growing up on the roof. And if you don't get that moss off there, that's going to create dry rot, and it's going to cause a lot of damage to that home. So what are some of the recognition features? This was what Highway E on-ramp looked like right over here prior to a little bit of work a couple years ago. And you can see they had a sidewalk along here, and they had a guardrail next to the on-ramp, and everything was just, sloping down. Your kid would have a hard time riding their bike along here without falling over. And that was slope creep, slope settlement, slope creep. And that's always a big problem with expansive soils because they're subject to expansion and contraction when you have weather cycles. So the way to avoid a lot of problems with expansive soils is to have somebody who watches their yard very carefully and has manicured landscaping and goes out there and watches it like a hawk. And you have some of those kind of people around. Even here in Raleigh, you got the provincial gardeners that are just out there watching stuff all the time. But the desiccation cracks are going to be a function of how severe the drying cycle is and what the plasticity of the clay component is. Now, there's going to be very few places where you're going to get pure clay. Most of the sediment on floodplains is silts. But a little bit of clay is going to control behavior. If you have 1% smectite clay, that controls behavior. Smectites are the really bad news. That's like catching HIV. You get smectites in there, give the job to somebody else. Run. Go practice somewhere else. Smectites they can swell up to 300 to 800% of their dry unit weight. They're generally altered tuffs, specifically in the United States, mostly of Cretaceous age. The bear paw, pier, all those that are so famous. What are the telltale signs of expansive soils? Well, you don't have to be a rocket scientist. You just have to have a little bit of training. And one thing is you drive by the residence and you look for stuff like this. You look for a heaving sidewalk or a heaving driveway, heaving flatwork. Flatwork doesn't weigh very much. Sidewalk going up to a house might be 3 inches thick if you're lucky on a good day. And so this is going to heave very, very easily. Whereas when it gets to the steps are a lot heavier per unit bearing area. So we'll do a cross section right here. So here's the shallow T foundation, let's say. It's a cheap place. And we got this big, heavy, front step thing sitting here with a little bit of a landing. That's nice and heavy. So it's going to hold down. The sidewalk's going to lift up relative to that if you have expansive soils. And so what you do is you walk right up and you look at that contact and see if you can see the old cold pour joint right here. This originally was poured against it, and see if it's moved. And that just takes someone to train you to show you how to do that. So very easy to see what the manifestations are. Now what gives you trouble is excessive watering. That's watering more than what the plants need. That could be natural or man-induced. Leaking irrigation systems. Now, leaking irrigation systems is a catch-22. Because when you're in expansive soils and you got plastic pipes, you're going to have leaking irrigation systems if you let it get real dry. That's just the fact of life, because it's a huge forces, huge tensile forces. So once you get a leaking irrigation system, you're off to the races. And the other thing is poor drainage. If you have some area that has poor drainage, you're going to have problems. Now, a lot of people don't start with poor drainage. They get poor drainage because of landscaping, because of the ground lifting up with half an inch a year, quarter inch to half inch a year, with root activity, root biomass, and worms. And so what used to be a 3-inch depression next to the house, 20 years later it's gone. And you got water ponding along there, even though it wasn't graded that way. What are some of the long-term effects? Typically, you'll see unreinforced flat work just busting up like this, like in the picture. And what you usually also see is poor drainage. You'll see downspouts coming down and water just ponding along here. If water's going to pond next to anything that's structural, you're going to be in for big problems. And poor drainage is very common when you're in flat-lying floodplains. So down in the river valleys, this is always a big issue. In fact, in a lot of river valleys, you have reverse slopes coming off the natural levees of the rivers. You're actually sloping the wrong direction on the lot because of the natural levees. And so you're going to have poor drainage. So when I say non-reinforced, that means it doesn't have rebar. They probably have temperature steel in it, which is welded wire mesh. Welded wire mesh, contrary to what a lot of contractors will tell you, is not reinforcement. That's just temperature steel. And it's not worth a whole lot. It's better than having nothing, but not much better than having nothing. Back it's close to having nothing. All right. Structural performance. First place you look, if you're suspicious of expansive soils, is the chimney. If you have an older place, you might have a chimney. Chimneys are nice and heavy, and they are going to settle and heave differently than a lightly loaded house. Lightly loaded, single-family residence, yeah, you're looking at 300 pounds per lineal foot, maybe up to 800 if it's a 2.5-story, big, nice Midwest house, but not real large loads compared to the chimney load. Chimney load can easily be 900 pounds per lineal foot or higher. And so you're going to see things going on along here, along this juncture, because you're going to have differential strain between the wood frame elements and the chimney. And sometimes if you have a little bit of bearing problem out here because they have poor drainage, the chimney will start tilting away and separating away from the house, and you're going to get dry rot down the back of that. Now, word of caution. Wood shrinks in cross grain significantly. 6% in cross grain over period of years, and 1.5% in longitudinal grain. So if we look at an older house, these wood elements are going to shrink, and you're going to tend to see movement here that's due just to wood frame shrinkage, especially if you got double headers on the top plates and on the sill plates. And so it's not all due to expansive soil necessarily. You do have to look at the framing system that they've used there. And if they're double plating, like with two 2x6s, you can have a 1/2 inch of settlement long term due to cross grain shrinkage. And that's a lot if you're going up against. Brick doesn't settle a whole lot, by the way. It doesn't shrink, The brick does not shrink. So if you have steel elements or brick elements or masonry elements, they're not going to shrink, but the timber framing is going to shrink. So you will get tearing between the two. Okay. This is what I was just talking about. If we actually look in here, you look at here is your toe plate, then you come up here to the first floor and you got 2 sole plates here, especially if you got a lot of windows. Doing the same thing up here. They may have a big header across here for a big opening. These guys are going to do a lot of cross grain shrinkage. 6% at each one of those. You're going to get considerable movement. And then if you look here, if inside the house you have a chimney or you have a masonry wall for the basement, and then you go to your timber and you have a steel stairway here going up with concrete steps on it, these guys are not gonna suffer any settlement difference. But the wood framing of the house will. This is actually what I worked on at Mount Vernon with George Washington's house. They had a big bow in it going across. What happened is, over on the perimeters, they had all the load coming down on the perimeters, and they had all these double plates and headers. And a couple hundred years old, those things shrank. And so the sides of the building are 8 inches lower than the middle was. And that's a pretty common problem with an older place. Now, if you go out, you're someplace like Texas, Colorado, South Dakota, where they really have serious problems with this stuff. They put in drilled pier foundations in the old days, and in the old days they didn't have continuous grade beams connecting all of them. When you don't have the continuous grade beams, well, what happened is you get these kind of problems in California and Colorado and Texas. And when you're dry, what you'll see is that you actually get a scooping down. You'll actually see a low point in the middle of the house. That's because they're watering out their yard out here and out here, but it's drying out under here, especially if they got it vented real nicely. And we kept increasing the venting in all of the building codes throughout the 70s, 80s, and 90s. And so here, if it gets real dry under here, especially if they have HVAC leaks and things in here, a lot of dry air, this will desiccate and sink. So that's typical of an extended drought kind of condition. Now this one is the one I saw more often, which was the interior was heaved and it was domed. We call this interior doming. And that's a typical long-term condition you get to 7, 8, 9, 10 years down the road. They're watering outside. Notice how the yard level is slightly higher than the crawl space. That's always a bad situation for entrapping moisture under the house. And so in this kind of case, you get interior doming. So nowadays we put internal tie beams all the way across here, and you want to have like a nice 30-inch tall tie beam. That's what I used on my house out in California, so that I have a big section modulus, MC over EI, to resist the bending, and tie all these things together. And then you're going to get much better uniform performance out of the structure. Now, perimeter, I don't know why this thing's there. Can I hide this? I want that out of the way. Perimeter lifting is a real typical problem when we have watering going on or poor drainage outside. And so we have these perimeter piers are getting swollen soils around them. They're heaving and they're lifting up. And you get perimeter lifting or edge curl first, and then you're going to get interior doming years later, maybe 7 to 10 years later. And these are actually accounted for in the International Building Code in Chapter 18 in the PTI manual, a Post-Tension Institute manual for post-tension slabs on grade on expansive soils. So you actually have to design, that's the controlling parameters, is edge curl and interior doming, because you're going to get a moment change when you go to interior doming later. So this thing's going to actually end up having a W kind of shape, and long as delta L over 180 isn't exceeded, you have tolerable tolerances for that bending. Well, here's what happens when you crawl under a house and you look inside of it. This is in Silicon Valley, San Jose. Typical here, they have these 6-foot deep piers. They have a 4x4 treated wood post here, holding up a girder, and you can see the thing's rocking. And they're in earthquake country. So you're looking at that going, how old is this place? Well, it's 4.5 years old. How much do they charge for the house? $900,000. $900,000, and I couldn't even get to year 5 without having framing integrity checks? No, wasn't able to get there. What's going on? Well, if you look at a cross-section in this area, what's going on, they had very, very wet area out here, and then they let it go dry and desiccate. And they had these little stub piers that are only about 30 inches deep, connected to a grade beam. And so as this dries out, there's actually a moisture suction effect going like this underneath, because this is all dry, so it's pulling the water out of there through suction and causing over-consolidated clay condition, and so the ground started sinking. And this lady had 3.5 inches of settlement in about a 6-week period. She'd lived there the whole time. And then here you also have a tilt, and the tilt is because of the progression of the drying front. So you're wetter over here, drier over there, so you actually get a tilt going like that. Anyway, this should scare you. This is not a good situation at all for lateral loading in a quake. This is typical of some others that I saw in the San Jose area. These are union-built tract homes, and you can see they're just getting racked all over the place. And down here we're crawling around and we're seeing all sorts of effervescent salts. We're seeing sulfates and carbonates and hydroalumina sulfates. The hydroalumina sulfates, like haliotrichite, actually melt in your hand. They look like little tiny, pretty little popcorn things with all these little little needles sticking out, and you take them and put them in your hand, and they melt in your hand, about 94 degrees. And so these salts are real typical of over-consolidated shales in dry areas because you don't have enough water there to wash all the salts out of the system. So you actually can have sulfate attack in extreme cases against the concrete. You have to have type 3C concrete if you have sulfates in the soils. Another factor you have to consider is variance in the frame loading. Typical tract house built like this is going to have heavier loads on the perimeter, and that's good because that's where you're going to have the most moisture change is out there on the perimeter. But that can also lead to differential heave because these guys aren't going to get as much load, so they're not going to heave they're going to tend to heave more than the ones next to them over here. Now we're going to talk about this over and over and over until I think you get it. So our enemy in geotechnical engineering is differential heave. We're not going to get rid of the swell, but what's going to do structural damage is when one part is lifting more than the other part, we're going to lose our functionality. We're not going to be able to open the doors up, open the windows, stuff like that, and we're going to have unhappy clients. All right, perimeter sinking. If the perimeter starts sinking, sometimes that also occurs during a drought because we have less moisture loss under the house, and the client rents the house out. The renters have a dog run back here. They're not home during the day, and so they just let the yard go fallow. So now we start getting all these big desiccation cracks, especially if I have a descending slope over here on a southwest facing exposure. This is going to get real dry. If I don't have any shade trees, watch out. And this is what you're going to get during an extended drought period. I had a whole bunch of these in Hawaii. And it turned out the biggest problems were on the west side, on the east side of all the leeward valleys, the east side of the leeward valleys. Now, people want to live on the west side of the leeward valleys because the west side gets the morning sunshine when it's cool, but the afternoon shade. So the folks that had the less expensive homes get the hot afternoon sun, and they bake. Well, the hot afternoon sun is going to do what? Right here. It's going to dry you out way more, and you're going to get more desiccation. So Honolulu Board of Water Supply told everybody, yeah, we're in a water drought situation here. Quit watering your lawns. So people quit watering their lawns, and what happened is they started seeing these kinds of situations where they're getting interior doming, and you'll actually see buckling right here, and buckling of the sheathing right there because this is dropping on the edges. Now, more common than not, when you start getting situations like this, you'll start finding, if you do a water level survey on the house, you'll start finding the house has a low spot. And the people call you and say, my house is settling. 9 times out of 10, their house isn't settling. It's the other side of the house is what? Heaving. Yeah, so you go in, it's just a relative thing. So you go in with a floor level survey, water level survey, or you can use a theodolite. You go in here and you see, oh, I got a high point over here. So as soon as you see a high point over here in your floor plan, in your floor level, go look under the house. And usually when you go look under the house, you'll find either 2 things: a broken pipe, a broken hose bib, something, and poor drainage, or both. A place where water's ponding here, so this is differential heave. This area is getting more water, so it's heaving more than this area over here. And that's your biggest enemy. 75% of the insurance cases I had with this kind of stuff were rental units. Because renters don't watch this kind of stuff like homeowners do. It's not their place. They're not invested in it. They're not tied to it. Okay. Let's take a little break right there. We'll take like a 4-minute bathroom break. We'll go on to the next slide. this semester with the new format, so I'm going to be moving along pretty well. Okay, past land use. I can't give you a lecture about all this stuff and make you think like, oh, geez, you just walk out here and look at these things and, you know, like Rogers has X-ray vision to see all these things going on. Frick no. You do your homework before you go out there. And part of your homework is you look at as many air photos as you can find. Air photos are much more reliable than people's memories. You can interview people, but people tend to have a memory like a log spiral. They remember stuff really well that's in the recent past, and as you get farther and farther away into the past, their estimates of the times get worse and worse and less reliable. So you got to look at the air photos and say, I got called out to a place in San Jose looking like this, where the house had a very regular up and down. It was that they had the floor slabs were cracking and heaving, just openly heaving, but it wouldn't carry on through the house. They were spotty. And I go, wow, that is weird. So I go back to the air photos, 1956, and it's an orchard. And what do they do in orchards? Well, they every 28 feet, they got an almond tree. Every 26 feet, 28 feet, something like that. And then they were tilling between the almonds. So you got loosey-goosey, expansive soils here, and you got rotten root balls here. And the way they solved the expansive soils problem back in the late 50s in San Jose was to bring in non-expansive fill to cover up a multitude of sins and problems down here. And they put in 12 inches of non-expansive fill. Well, it's like they're building a road. And that was the kind of pavement sections people looked at back in those days. 12 inches today seems like laughable. But anyway, that's what they did. So they brought in 12 inches of fill, and then they just slab on grade, right on the ground. 4-inch slab. And what did they do with the root balls? They left them there. So what happened is, down the road, you get these pockets that have higher soil moisture content, and that gives you the differential heave. And then you start getting differential heave, and what happens to the pipes that are embedded in the slab? They break. So the only way you putz around on expansive soils with slab is, two ways. One, pre-pond the site for 4 months, 6 weeks to 4 months, and then put in a Helfer stout section, 14 inches, something like that. Something that's big and beefy and bomb-proof. And now, that seems like a lot of concrete. That's less concrete than the first letters from your attorney writing back. Attorneys don't do anything for less than about $2,500. They don't even blow their nose for less than that. So it increases the cost of the foundation some, but it makes it a much more resilient structure. All right, asymmetric landscaping practices. What are other things that I saw? This is the classic. This is the classic. They let the backyard go. They get desiccation fracks. The backyard may also be on the sunny side, on the southwest exposure in North America. And then on the other side of the house, they got shade trees. They got watering going on. This is asymmetric landscape. That's engineering work for, letting the backyard go to hell and letting the front yard look nice. Now, a lot of people do that. And so what happens here is you're going to get moisture on this side and desiccation on the other. So you're going to have heave on one side, settlement possibly on the other side. So you're going to have problem. And what happens is you're going to have leaky water lines, sprinkler control boxes, and leaky hose bibs over here on this side next to the sprinklers that are really driving all this. So if they have a leaky hose bib right here, you're going to get this mound of water coming off of it. It looks just like I'm drawing it here. And one half of the house is going to lift up 6 or 8 inches. That's just hard to get away from. All right. So that's some aspects, some basic engineering aspects of expansive soils. Let's see what I have next here for you. Okay, expansive soils promote slope creep. So we go out in the forest and we see these butt-bowed trees come down and turn in, like you see all of these right here down in Tennessee. This is along a Shawnee Ridge between Memphis and Dyersburg area. all that slope is moving around all the time. And here's a case where we have a slope in a Cretaceous age siltstone, Panoche Formation. It's graded 1954 with a mid-slope drainage terrace that's 10 feet wide, and then a 10-foot high brow ditch going up above the cut. And now I want you to notice this. This is the right-of-way. There's the county or state right-of-way line going up around the cut. Now, you come by and look at it, 1983, so we're coming out there 29 years later. There's the fence, and that's all you can recognize there. So what happened? Well, this has enough plastic material in it that all this nice cutting you did here is all just kind of slowly melted away, and it's gone. So the drainage infrastructure that you put there is gone because of plastic creep and shrink and swell, shrink and swell, shrink and swell. So 30 years of time, not very long, but we don't have a good way of handling this kind of stuff with short-term soil mechanics tests because every site is different. We have a large descending slope here that goes up hundreds and hundreds of feet above us, and so that's a kind of problem that's an aging problem.
I have a question.
Yes?
Was the vegetation put there on purpose?
No, that's all just strictly volunteers. Strictly volunteer vegetation. So this is coyote brush, and these are black oaks that have just come in that area. And the reason is you don't get black oaks back over here because you got cattle grazing here, and the cattle eat the black oak shoots. So when the cattle are introduced to an area, that immediately precludes new things growing if the cattle can get to it and eat it. Notice also that the farmer is mowing here for a fire break around. So that's going to tend to break up the soil and cause more moisture infiltration up around the cut, which probably helped exacerbate the situation. Now this is from CFS Sharp's textbook back in 1938 called Landslides and Related Phenomena, and he actually talks about slope creep. Now slope creep has an engineering definition, and so I always can tell engineers from geologists. The engineering definition of creep is strain under sustained load. So if you put a sustained load on something, it's going to deform under that sustained load. Now the problem with creep is the downslope creep is a function of slope, height, it's a function of slope inclination, and it's a function of when I say slope height, I mean the length of the slope, and it's a function of the plasticity of the materials and a function of how severe the wet dry season is. Now, you're never going to get a wet dry cycle that's going to be exactly alike, ever, 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 ever. So when somebody says, and I've had a lot of people come in and tell me, well, we know what the depth of seasonal creep is here, it's 30 inches. Well, 30 inches is the number you use. I doubt it's 30 inches every single year. Hopefully it's 17 one year and 37 the next year, and the average is maybe 30, but that's dangerous. I mean, I've seen lots of desiccation fractures deeper than 12 feet. That's not unusual at all. So it's a tough thing to model because you have a lot of assumptions that you're rolling into it. And obviously if you have a point source of moisture, like a leaky fire hydrant or a leaky elbow on a water line or something, that is really going to exacerbate the situation. And you won't pick those things up with sonic velocity log testing. That only picks up the big things. You won't pick up tweaks that are just weeping, don't make any noise, like you get at elbows and at T's. So when you're up in the areas like this, that's a big problem in Honolulu. They got lots of things creeping down the slopes. When I found the hot zones that were really creeping a lot, they were always broken pipes, corroded pipes, and they were just weeping. You know, they didn't have the sonic velocity testing. They didn't hear anything. Well, you don't have to hear anything to get a million gallons a year at one spot. That's just a little drip, 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 drip. That's 1 million gallons a year. You can do the math on it yourself and figure it out. So this is typical. What other things do you look for? You look for broken retaining walls. You look for tilting headstones. You look for tilting fence posts. butt-bowed trees. Isolated blocks that have moved off from where they used to be and are just floaters. You look for tilting telephone poles. And there's another floater block. Real typical. Now, the other thing you need to realize is strain accumulates upslope as an integral function. This is about as mathematical as Uncle Dave's going to get with you. But this is why you need to have calculus. Kids always come in and say, what do I need to take calculus? Well, for my courses, this is the only reason you need to understand calculus or calculus concepts. Delta x1 is down here at the toe of the slope. Delta x2, delta x3, delta x4, delta x5, all up here. The time you get to the top of the slope, it's the sum of all delta x. We're going to see that later in chapter 6. So slope is strain is accumulated upslope as an integral function. So you can get away with murder on a little slope that's 10 feet high and do all kinds of things that you can't do with the same material on that same slope going 500 feet high because of the accumulation of strain. By the time you get on a slope 500 feet long, that strain accumulates all the way up there, the retaining wall at the top has moved a couple feet and is tilting over. So scale is very important to what we do on this stuff. You have a long descending slope, get your butt away from it. Don't put your structure right out there on it. You're going to be in the influence area of that slope. Just draw a free body diagram, and you'll see. Okay. Here's a typical slope creep problem. I got called out on it. You have an apartment building right here that has this protected balcony around it, and you say, why do they got the balcony all shut like this? Don't they want to see the view? No, this is California. That's a hot tub. They're naked in there at night, having a good time, tickling each other with peacock feathers. They don't want to have the view. They have their own view in there. Okay. Anyway, so this comes out, and what was happening here? The owner, by the way, his son lived here, and that's how I got called out there, because the owner, the son, had some vibrations going on here, he said. I said, yeah, I know you have vibrations. I know what you're doing up there, kid. He said, it's getting worse and worse. And I said, stop having sex. It won't get worse. But what it was these things were moving on him, and so he was losing the support. And that was because somebody came down here and cut the slope after that place was built and accelerated the creep of that zone. This was a overconsolidated clay shale, a Pliocene age unit. Here's the typical of butt-bowed or pistil-butted trees. These are aspens. Everybody loves to use aspens because they grow like weeds. This is on Dunkley Pass in Colorado, around 9,500 foot elevation. But these things, this is a little road cut here for the highway, and so these things are showing, very, very high rate of creep in that zone of the cut. Now, as you get away from the cut, you get away from the severe pistil-butted trees. So you want to be looking at the trees. They're going to tell you a lot of things. These trees aren't very old at all. Here we are in the Grand Canyon, and here we're going to see how slope accumulates upslope as an integral function. So we look down here where the channel is cut into this schist. This is the Vishnu schist. And so you have let's see if I can do this here. This is the foliation dipping about 70 degrees, and we come up here and we see the thing turning over. It's a toppling failure. We call this a flexural topple, but what I want you to notice is this is where it's initiating, down here in the bottom of the channel, and as you go up, you see the hinge line getting deeper, 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 and you see this thing coming up and then turning over, and it's getting more severe, more severe, more severe, very severe. That's the integration as you go up slope. Now, if I put a slope inclinometer right here, and I put one right here, and I put one right there, I'm going to get 3 different answers. 20 years ago, 22 years ago, I went to China for the first time. They were putting inclinometers in there, and they said, oh, Dr. Roger, we want to show you, we got these slope, and some part of slope are moving a lot, the other part not moving so much, always upper part moving more. Well, the upper part's moving more. It's the same darn slide. It's the integration of strain upslope. And they're experts in this stuff now, because they go out and do a lot more instrumentation than we do, because they don't have a lot of money to spend $1 billion here and $1 billion there on slide repairs. They got so many slides, you can't repair all of them, so you have to decide, it's cheaper for them to move the highway than to repair some monstrous slide. So you're going to have different depths of movement and different amounts of movement, even though it's the same slide feature. And that's how slope creep works as well. So the place I got to be real careful is right up here, because I have the accumulation of all the strain going up the slope. All right, how do we look at this mathematically? This is what I did for the Chinese way back when. I was looking at these things and saying, well, we got these desiccation fractures. If we look at them as a discrete element of soil, we can actually try to simulate that as a load coming on our structure, our basement wall or our retaining wall, by doing this kind of a analysis. And so desiccation cracks more or less form normal to the slope surface, and you're going to get a load that's basically an inverted passive pressure diagram pushing against your stiff element down here, either your pier or your wall or something down here. So you have to design for that slope creep load. Now if we look at it, when something shrinks and swells, it swells going up more or less normal to the slope, but when it shrinks, it comes straight down. That's the increment of strain. So you started here September of last year. By September the next year, you're here. The next year, you're here. And it's never exactly the same year to year. It depends on how severe the weather cycle was in that particular year. But that's what's going on. Now, when do you see most of the creep? During the swell cycle, believe it or not. You think it would be during the dry cycle, but no. When I put an inclinometer in here and the hill starts getting wet and starts heaving, that's when I see the downslope movement. It's on this cycle right here. So you'll go from being right here to over here. And that's because your inclinometer goes down into something that's not moving. That's the fundamental basis of an inclinometer. The base of the inclinometer has to be in solid rock that is not part of the landslide, is not moving, because you're measuring everything relative to that position. If you don't get it down deep enough, it doesn't work. And the other problem with inclinometers is you have to have all the readings at precisely the same elevation in the hole, which is impossible when this thing starts bending over. So you have systematic errors that are always going to be there in your inclinometer readings. 95% of the inclinometer readings in this country are misinterpreted by geotechnical consultants who don't know any better. If they see an offset, they get all excited. You put an inclinometer between a highway fill and bedrock, you're going to get an offset. Why? Because you got different materials with different E's. You know, if I put a whole bunch of toothpaste up here and I have this hard table here, the toothpaste is going to move around. That's how fill is compared to bedrock. So under the sustained load, one of them is going to move a lot and the other one's not going to move a whole lot. So you're going to get an offset between them. Doesn't mean you have a landslide. It means you have differential strain. That's all it means. Okay? So this is the model you want to keep in mind. It's a conceptual model. Okay, so what do I have to know about this stuff for as an engineer? Well, here's why you have to know about it as an engineer. So all you geologists can go to sleep now. We're talking just the engineers here. And we're going to have we have a structural element, a foundation, in this near surface zone on a descending slope. And long term, there's what my creep vectors look like. And they're going to be a log spiral shape. So I can approximate that very easy with a triangle. I just have to guess how deep the triangle is. That's the engineering judgment part. That's the part you pay $250 an hour for. Okay, because that's some guesswork involved. And you can do a trench along the hill and figure out where the creep zone is pretty easily. You don't have to be a rocket scientist to do that one. You just dig a trench, come right down the hill, you'll figure it out. It's pretty easy to do. But what happens is long term, you're going to get passive wedges that are going to build up as this soil slowly pushes down, and finally it's going to hit this element 10, 20 years later, and then it's going to heave upward and shed some of the load. So you're never going to develop full passive, but you can approximate it by using an inverted passive diagram. That's what I used to do in practice, because this is what you're actually going to get, like that. So if you don't do that, this thing's going to get loaded up. Now, if it's reinforced concrete, you got some things going for you. Reinforced concrete increases its modulus with time. if you kept the mix at a good, 0.45 water cement ratio. If you make the mix too wet, then it's not going to be as good. But it's going to tend to harden with time, and so it picks up load down the road. There's some compensation. If you make this out of masonry block, you're going to be in trouble. Most of the problems I go out and look at in Rolla, where they say, and some of them are civil engineering professors. They say, come on, look, my basement wall is moving. I think it's bowing outward. Well, they're always masonry block. Why? Because a 9-inch wide masonry block wall with a number 4 bar sticking up the middle of it has about 25% of the moment capacity of an equivalent section reinforced concrete wall. The only reason you do anything with masonry block is because it's cheap. So you save 40% on cost, you sacrifice 75% on strength. So if you got German blood in you like me, I'd go with the strength. I don't want the cheap shit. I want the strength, yeah? Okay. But you can save money. Now, have I used masonry block? All the time. I use speed block all the time, where I'm going underground and I got to do a mine closure or something. I have to have small blocks and I have to get them in there, and where I'm keeping it in compression. Great for compression. It's okay. Not good for bending. Well, it's cheap. If you're going to do a block wall, by the way, put all kinds of drainage behind it. You never can have too much sub-drainage. You can't have too little. You never can have too much sub-drainage. Never can have too much sub-drainage. Okay? All right. So we're done with that little vignette. I'm going to get in trouble. This is all being recorded. I know. All right. Part 3. Part 3 is not real long, but it's real important. Oops. The biggest problems I've had in my practice have all been overconsolidated clays. I could teach a whole class called The Perils of Overconsolidated Clay. Why? The shales. Shales have been compressed tectonically. They've been taken down way in the bowels of the earth. And clay has a memory. It's intelligent material. You can't take too many clay mineralogy courses, because clay is always going to bite you in the behind if you don't understand it. And clay that's overconsolidated tends to lose strength with time. So let's look at normally consolidated versus overconsolidated clay. What you get in school, they draw things like this, and they're nice and easy, and you can absorb it all. And if you took your mechanics of materials courses, you go, oh yeah, I remember this. These are Mohr circles. There's more or less, right? And there's a Mohr circle, and then you plot these things at increasing levels of confinement, and you bring this line down the failure envelope, and you say, that's phi. That's the angle of internal friction, and this intercept down here is the cohesion. And that's the kind of stuff you need to know to pass your engineering examinations. And that's about all you need to know it for, because this lies like crazy. I wish it was always this simple. It isn't that simple. And most of the time, you're dealing with overconsolidated clays. What does that mean? That's a clay that's dried out. And when it dries out, it'd be like my body dying and getting mummified. Is it going to change? It's going to... We have all these incredible suction forces as all the fluids drain out of me. And I'm going to pull tightly together. And I'm going to be a hell of a lot stronger per square inch than I was when I was filled with all this water. Now I know this because I was the youngest of a group of boys. I had nothing but brothers, no girls in the house. See? It was all jockey shorts. And what do boys like to do? Two things. They love to fight and they love to wrestle, because you test your manhood that way. And we grew up in an area that was it's adobe soils. So dirt clods. We were always throwing dirt clods. I was great at throwing dirt clods. Man, we'd throw those things. And the summertime, you get hit right in the head, side of the head with a big dirt clod. It hurt. That's a desiccated soil. But in the wintertime, you could get a big mouth and really live dangerously in the wintertime, because that guy's just going to throw you a big hunk of mud at you. And that mud, it gets all messy, and your mom gets all mad and everything, clogs up the washing machine, but it doesn't hurt. That's desiccation, see? Desiccated soil, strong. You can build big things on it. Got great bearing capacity. Long as you put a roof over it and keep the water off of it, you'll be fine. I don't know anybody putting roofs over fill embankments, but that's what you'd have to do. And a subdrain underneath it. Because the strongest it's going to be is the day you put it in. And from there, it's a downhill slide. So what's going on here is you actually have a apparent cohesion down here in an overconsolidated clay. And that apparent cohesion is very important. But you can lose it if you shear the specimen repeatedly. You can actually see this thing. This thing will just fall off and drop. And that's what you have to watch out for. So you actually have a effective C sub E, and you have an effective phi angle for drained conditions, long-term drain conditions. So if we actually take a direct shear test, we look at ASTM D3080, standard, cheap direct shear test, you can shear the specimen at 0.05 inches per minute. That is fast in the world of clay. I'm talking permeabilities 10 to minus 6 and lower. That's really fast. If you took that same specimen and instead of shearing it over a period of 30 minutes, you did it over a period of 30 days, which is like it is in the real world, in the field, you're going to get a whole different answer. Whole different answer. Because you're getting pseudo drainage while you're shearing. And you're going to have this kind of a diagram instead of that kind of diagram. And you notice the phi angle here is a lot lower than the phi angle here of the rapid shear test. Yeah. So normally consolidated clay only has meaning when you're constructing man-made embankments. Otherwise, forget about it. Don't even look at it. It doesn't exist in my world. It doesn't exist in the geological world. It doesn't exist. It's gone. Okay, here's the problem. Overconsolidated clay is going to come down. Look, here's my data point. These are real data. Look at that. See, real data never lines up like it does in soil mechanics textbook. It's always kind of... That's what's great about doing laboratory testing. If you do laboratory testing, you find out, gee whiz, this stuff has a lot of variability. Yep, it does. A lot of variability. So it's going to come down, and you're going to take this line, and you're going to go, oh, there's a cohesion. No, that's not the cohesion. If it's overconsolidated, there's a cohesion. It's got big cohesion. Remember those dirt clods hurt Dave's head? That's the big overconsolidation. So I'm going from this strength, 3 times, threefold higher. So I'm coming down here and then skating across like that. So I'm normally consolidated from here on up. I'm overconsolidated from here on down. Now, you get to places like Cleveland, where they had glaciers 3,000 feet thick going up the Cayuga River Valley. That's really overconsolidated clay. So that clay has had this huge load on it that's melted away into Lake Erie, and now that clay can rebound with the removal of that glacial load and absorb more and more water. And it's stabilized for the environmental conditions to which it's subjected today. And everything's fine till you make a cut in it. You go out there and make a cut, now you rapidly unload it in a couple hours, and all of a sudden it's going to heave, absorb moisture, and start moving around on you. And once it starts getting a slip surface, you can actually see 80% strength loss. That's scary. That's what happened in the Panama Canal with the Cucaracha Shale. Now, the most important slide I'm going to show you in Chapter 5 is right here. So let's camp out on it and spend some time on it. This is the most important thing I'm going to show you. Differential swell. Okay? Let's say, and I had this happen with a paint factory in San Jose. This building had a huge monster slab on it, 12-inch slab, double reinforcement, number 8s at 6, 2 layers. Should have been able to withstand B-52 bombing raids. Slab was breaking up like crazy. Why? You can't have uniform resistance to soil heave. The guy that designed that slab designed it for all these forklifts running around carrying paint. Now that's the heaviest structural loads you're ever going to have. If I took all of us together, and I used to do this before political correctness came in on us, but I got all the boys and girls and pushed us all over here in the corner together and got real close. And then I asked you for all your respective weights. which the girls don't usually give, but anyway. And we added up all of the weights, and we divided by the triangular area here that we're all squished into. We get about 35 PSF, 35 pounds per square foot. That's not a hard thing to design for. Now, if we had basement of a hospital, what do they keep in hospitals? Well, yeah, not more. Yeah, morgue too. Yeah, the morgues don't weigh too much. No, file cabinets. What do you think file cabinet bearing is? Want to take a hazard a guess? May? 10 times higher, about 300 pounds per square foot. So that's the biggest load you design for until you do a paint factory. You know what the bearing is on a forklift? Anybody want to guess? 400 PSI on a hard-wheeled forklift. Those are the hardest things you can design for. That's why at Walmart they have to put in that topping layer. They have to really design it strategically because they're running around in these Home Depots and Lowe's and Walmarts with these very high concentrated loadings. They have to design a topping layer in there with a material that has a hardness of 7.4. They use this Missouri St. Francis Mountain rhyolite. Mix that in there because they can't have divots in there. The whole forklift could flip over when they go way up high to store things up on the top shelf. So the paint factory was designed for the forklifts, but the guy ignored differential swell. He said, well, it's going to be uniformly loaded slab. I'm going to lay this out very carefully. It's going to be uniformly loaded, so I shouldn't have any soil mechanics problems. I looked at the guy like he had AIDS. I'm going, are you kidding? Let me draw a picture for you. So I drew this picture for him. You don't have anything. Uniformly loaded slab? Yeah. Okay, let's look at that uniformly loaded slab. Let's go underneath the corner right here. Let's draw, it's like professors love to do this. You come down here and you draw a little cube right here. That's an element of soil. You ever seen an element of soil? I haven't yet, but anyway, they're down there. It's an element of soil. Now, what's looking down on that element of soil? In this quadrant, we have the load of the building. In this quadrant, we have air. In this quadrant, we have air. And over here in this quadrant, we have air. We don't have a hell of a lot of load on them. That's the lowest load you're going to have is underneath the corner of the building. Because 3/4 of the area is just atmospheric pressure. Now, come down the side of a rectangular slab. What do we have right here? We'll go get a little element right here, 10 feet below. And half is loaded, half is unloaded. But now we're going to go to the middle of the slab out here. All 4 quadrants are loaded. Well, here you go. There's the corner. There's the side. There's the center of the slab. That is the soil heave load on your uniformly loaded slab. All negative moments, all edge curl. The guy did it all bass-ackwards. Didn't have a good geotechnical consultant either. Here's your problem. At the center, you're only going to get this much swell. Out here, you're going to get a whole lot more swell. It's all a function of area of dead weight. So when we go out into Texas and Oklahoma and we rip out 42 inches of expansive soil and put in a whole bunch of gravel, we ain't putting it there for drainage or bearing. We're putting it there as dead weight to hold the shitty soil down. That's all. Real advanced engineering. Dead weight. Hold it down. Because if you hold it down, it's not going to heave as much. That's as complicated as it is. We can, that's it. So what's going on here, if you get nothing else out of this, is there's your problem. So where do the big piers have to be? Where are the most important piers on that building? On the corners. Thank you. Better make them bigger and deeper and tie them in nicer, because that's the one that's going to have the most pull put on it. Piers aren't there to hold it up. The piers are there to hold the corners down. You would not believe how many geotechnical engineers in California spec piers on their project and don't know that. And I would review them all the time, and I'd say, especially when I was younger, I'd say, why do you do this? Because we've always done it that way. Oh, that's not an answer. Why is the pier 8 feet? Because, we used to make them 2 feet deep, and that didn't work well. So then we went to 4, and that didn't work well. So then we went to 6, and now we're at 8. Now they're at 16, 18. But they couldn't tell me why. Just that, That's how we've always done it. That's how we've always done it is not a great answer. That's kind of scary. You should know why you build something the way you do. And it was actually a guy named Bob McNeil who did a thesis on that back in the 50s with Woodward Clyde in Danville, California, that came up with a concept of the drilled pier and grade beam system. And what he did is he put in a 2-footers and 4-footers, 6, 8, and 10, and then for that particular year, 1956 to 57, 6 seemed like it worked. And what he forgot was what? What did he forget? No 2 winners are what? Ever alike. Yeah, that was one cycle. And it was probably an average cycle. And so the 6-foot piers didn't work as well as everybody had hoped they would. They found that out later. Okay, so that's what I want you to know. Over-consolidated soils can lose strength. They lose their cohesion when they get re-wetted. So if you disturb them or you re-wet them, they forget the memory when they heave up again. So you got to be real careful when you're dealing with over-consolidated materials. All right. What do we do to mitigate these things in the time we have left? How do we mitigate problems on foundation, problems with expansive soils? Well, one of the things we do is we get young geologists who we can hang off ropes and send down holes. We don't get claustrophobia. You recognize that? Right. Okay. What are some of the things that have been done over the years? One of them is pre-pond the site. This is what my dad did down in Orange County. Very hot, expansive soils down in Mission Viejo. Those have performed better than any other cheap approach I've ever seen. And the reason is because down in Orange County, they overwater everything to keep everything green and lush and pretend they're in Hawaii. And they're on the coast, so they don't have as big a seasonal cycles as you get further inland. And so it works. What you don't want to do is go from a dry to a wet. The wetter it is, when you build it, the better you're going to be. You're going to get less heave. Now, another thing was, put post-tension or put cutoff walls on the slab on grade. This turned out to be more problematic because you get more uplift on these when you do get water over here next to the structure, and it tends to edge curl and lift up more easily. You can put in non-expansive fill, like pavement engineering, over to hold the dead weight, to hold the bad soils down. Or you can use pier and grade beam systems and hope you don't have one side that catches more water than the other side, so you don't have to, and you have a redundant enough system to resist differential uplift. I'm going to talk a little bit more about this one, because this is not foolproof as you might think it is. I thought it was foolproof when I was in school. Other solutions that have been used is to use over-steepened over-excavation under where you're going to have the houses and put in lots of non-expansive material over the top. Try to bury your expansive soil as far down in the valley fill as you can, because the more dead load you have on it, the less trouble it's going to give you. It's not going to harm you if you bury it down there 40-plus feet down. It's not going to hurt you down there. You do want to have sub-drainage beneath it. But that's a pretty good solution. Now, this kind of solution can work well for you if you're taking the soil type material out, hogging it out first, and filling in the valley bottoms with that. But you have to over excavate the bad materials out of here, the clays that are down here. You have to over excavate those out and then roll them back into this thing so you don't cause consolidation of those materials. We cover that in the 441 class. The theory of drilled piers is that you extend these piers below the zone of seasonal fluctuation. So this is the dry season, this is the wet season. Some might come all the way up to the ground surface. But those piers got to be deep enough so that when things dry out, you don't get a loss of adhesion along 3/4 of the pier. When that happens, the pier will drop and you'll break the grade beam. And how do you solve something like this? Go in here and put some soaker lines in and heave this back up. You see this happening. My dad used to do that all the time. He'd go out there, somebody would call and complain, and he'd find, yep, they let one side of the yard just go fallow and get real dry. What you do there is you come in and you bring this back up, even if you're under the house, and then you seal it off with something like visqueen so that you aren't going to lose all the moisture out of it again. All right, so here's the theory on going from the dry time of the year to the wet time of the year. You have to extend this thing down far enough that you have enough adhesion along here. Typically 250 pounds per square foot up to 750 pounds per square foot, typical numbers for skin friction values on these things. And then one of the problems you get up here, if you're drilling, especially in a desiccated zone, you'll tend to get mushrooming of the piers. Now, mushroom piers never good because that allows this soil, when it gets wet right here, that allows it to push up and get more uplift. So if you allow mushrooming on the piers, you diminish the pier's ultimate capacity. So you're trying to develop load carrying capacity through skin friction down here in this lower zone where things aren't changing. You're trying to resist the change in load, the uplift and heave, in this zone right here. So this has to be deep enough below that to resist those changes. That's the theory. So what are some of the dumb things people do in expansive soil sites? They do all kinds of dumb things. First one is they grade it with less than 2% grade across the lot. And then they have a crawl space that's lower than the yard, especially after all the landscaping. They bring in sod and things like that. And now you're going to tend to get water trapped down under the house. And later they'll put in a sump pump. And of course the sump pump will go off when it gets burned out because the pipe's too long, the hose is too long. Hose can't be longer than 60 feet if you look at the limitations on the pumps, and sometimes they'll run at 150 feet. They don't read the directions, so they'll burn the pump out. And then, of course, the pump goes out when you have a big lightning storm and big rainstorms. Pump goes off, the water gets in there anyway. The crawl space is lower than adjacent yard, you're in trouble. Pier cuttings are often piled up in the crawl space. When I used to crawl under these places, I'd see all this, loose garbage soils. Well, that's from the pier cuttings being brought up and just spun out on the ground. Well, that's not going to help you at all. And then shallow, unreinforced piers. One number 4 bar is not reinforcement. That's just temperature steel. And it's not going to help you. It's not going to give you much load. 2,000 PSI max, or 2,000 pounds tension is about what it's going to take. And it's going to pop. And a lot of times these things will break. They'll actually snap. The steel will be there in the middle of it, but the pier will get like a 1/2-inch crack in it. And then it's not working anymore. They didn't expect over-watering or stupid landscaping practices. That's what the soil engineers would tell me. I didn't expect them to do these dumb things, like not turning their water sprinklers off when we get into the wet season. Well, people will do that. They are stupid, especially renters. They don't care. So variances in landscape watering between front and backyard and side yards also. And isolated piers. What I'm showing you here are isolated piers. These never work real well. Isolated piers can move around and they don't shed load off to the next adjacent pier. They don't have much redundancy at all. So if you want good performance, you really got to tie the piers together with a nice deep grade beam, which I mentioned to you previously. A lot of that stuff's beyond the control of the project engineer. So how do you handle this thing? How do you design in depth? Well, you put in continuous grade beams with a high MC over EI, high section modulus. You get 5% drainage away from the house, not 1%. You put in big yard drains that can take 24 maple leafs and not quit working on you. So you have a redundant, you should have seen me when I first got in practice. I put in little yard drains like this. You buy at Lowe's, the 8-inch ones. And the longer I was in practice, the bigger and bigger my drains got. Pretty soon I could swallow up Volkswagens. I put in big drains. Why? Because 2 maple leaves can plug an 8-inch drain. No problem. Just 2 leaves, middle of the night, and the drain won't work. The drain will be clogged. So you want to watch all your grades. You can put in a polyethylene moisture barrier. beneath the house. So once you get this stabilized here, you want to put something in there to stabilize that soil moisture so this can't dry out too much. Now that's not hard to do. Piece of plastic sheeting will do that. 10 mil polyethylene vapor barrier. So what we want to have is fewer piers of greater diameter and greater depth. So instead of having a bunch of little piers, you're better off with maybe just 3 lines of 18 or 20 foot piers with a big grade beam between them. And most of these things that I harp about here have been implemented now in Los Angeles, Orange County, and San Francisco Bay Area. All right, still got a few minutes left. I'm going to try and go on to the next one here, which is depth of seasonal variation. How do we tell what the depth of seasonal fluctuation is? I used to get in a lot of arguments about this and doing the review work, because my firm did lots and lots of review work, initially for the city of Los Angeles, and we were training their people, and they would tell us, these are the arguments we get into. We want your technical expertise to help us in this. How do we tell what the depth of seasonal fluctuation is? Well, one of the easiest ways is to simply look at the moisture content variation of the soil with depth going down. What you'll see is, you'll see something when it's over consolidated, you'll be coming up like this, you'll see it max out right here, and then this is the zone of desiccation. So here you can say, well, for that particular year, that's how deep it is, and let's say it's 6 feet. And that's going to be a minimum number. Then you have to estimate, well, how far do I go past that now? Here I am with a meter stick, pushing a meter stick down in these desiccation cracks, and it's just, just a couple centimeters under a meter. So that's 38, 37, that's over 3 feet. And we had all sorts of people telling us in this same community that the depth of seasonal fluctuation was 18 inches. Now, not when you see desiccation fracks that are 2.5 inches, 3 inches wide. It's a lot more than 12 or 18 inches. What are some of the problems? Well, when you do drainage improvements in this kind of environment where the slope can heave, you're going to get all kinds of desiccation rat holes underneath your V-ditches. So the water coming through here cannot get into the ditch. It's going to get underneath the ditch. That's what happened right here. Then the slope heaved, and look at the offset right here between the down drain, and it's offset about 4 inches right there, because this got put in the dry season. And if you put in your concrete drainage work and flat work in the dry season and you let this get too dry, now when it gets wet, you're going to get noticeable heave, and it's just going to break your concrete flat work. So it's not fun to go out there and put it in, but the wetter the slope is when you put it in, the better. So what did I do in those kind of situations? I keep sprinkling the slope. That's what I did. I want the slope to dry out before we get the V-ditches in. So we go out there with sprinklers and sprinkle it. And because we don't want a bunch of desiccation cracks growing in the slope, because we're going to have a big heave cycle if we allow that. All right. Next, shale beds, swimming pools. We might not get through all this, but this is some stuff you're never going to find in a soil mechanics textbook, so I want to show you. This is a real typical Orange County job. Everybody in Orange County who has much property, as in more than 10,000 square feet, has a swimming pool. And the swimming pools all weep water. They're made out of gunite. And then they have a lining in them. But they all have water that percolates through the gunite lining. And this is pretty typical. You'll see these huge cracks in the flat work around the pool, and then noticeable settlement coming down here behind a wall. What's going on here? What can we do about it? Well, you have several things can be going on. One is, if you have isolated shale beds, you're always going to have a problem with differential heave, and it's going to look like this. If I did a floor level survey over this kind of a site, and this was a condominium unit in Pleasant Hill up in the Bay Area, this is what your uplift pattern is going to look like over that. Right here you're going to have sky high heave. The maximum is going to be right there. And then you have more and more confinement over here, so the amount of heave is going to change. So these seams are always going to swell asymmetrically. These are what give you nightmares on highways. If you go along State Route 118 through the Simi Valley, they got some beautiful little shale beds coming up there, and you just go, oomp, oomp, oomp. That's a great ride. If you can catch it, at the right speed, you can really get a nice bouncer out of it, So that's really probably, here's where you really got to have the engineering geologist out there with his eyes screwed on saying, hey, we got little shale stringers in here, 3 inches thick. The soil engineer's going, 3 inches, so what? We'll be putting piers through it, no big deal. Guess again, can be a real big deal. If you got any smectite clays in here, you're hosed. You have to over-X down about 6 feet, backfill this with something else. 6 feet's a minimum, or it won't work. Here you go. There's differential heave. That's what it looks like. You don't have to have a PhD from Rolla to notice it. See, right there? All you have to do is skateboard blindfolded at night. You'll find them. They're there. Bloop, bloop, bloop. They're called whoop-de-doos. That's a scientific term. Whoop-de-doo. Some of my foreign students aren't getting that one. Okay, well, here's the one I had in San Jose. This is a guy who worked for Lockheed Space and Missiles. Fastidious aerospace engineer. And he's building a pool, but he's in San Jose. So in San Jose, how far is the pool from the house? 8 feet. But he says, I'm not going to have any problems because I'm going to seal everything up with structural concrete and mastic. And he really did. I mean, this guy was, it was something, And the back of his house lifted up. And boy, was he mad. He was fit to be tied. And he insisted that State Farm go get me, get somebody with a PhD to come in here and, see what's going on. And he was suing the soil engineer and suing the contractor and suing all these different people. And what you have here is you have more hydraulic head in the middle of the pool. So 85% of the seepage is right here. It's out the bottom. So it's going to go down, and this is partially saturated down here. So it's going to go down and be chemically adsorbed, with a D, adsorbed. Clay loves to take water and go, just like the IRS in your paycheck. It never gets enough. It's just eating it up, eating it up, eating it up, sucking up that water. And so this has nothing to do with hydraulic conductivity. You hear that? Hydraulic conductivity has to do with saturated conditions. This is unsaturated soil mechanics. And this goes very fast. This is like watching, a pipe break in a dry fill. And you can just watch that thing moving every minute, very, very rapidly. It's chemically adsorbed. Okay. And so this thing is spreading out, and you get about 15% or 7.5% off each side because you got diminishing hydraulic pressure as you come up, less and less water depth. And so you have some water coming out here, but not nearly as much as you have coming under here and coming up. And it was just this outside line of stub piers, these are only 42 inches deep, that lifted up. And that was enough to drive him nuts because his bowling ball was rolling across the kitchen. Kitchen was in the back of the house. This pier did not go deep enough to get lifted. So it's differential heave, once again, that drives you nuts. So if you look at it, that's what the flow net looks like. So you have this water coming down out of the thing. You have this one coming along. And we picked this up with cone penetrometer. I love cone penetrometer with a temperature gauge. It's the most accurate tool in your tool chest for seeing the zone of saturation when you're out putzing around structures. Because as soon as you go right down right here, as soon as you hit the saturated zone, you'll see a 6 to 8 degree change in 1 centimeter. Boom! You know right where it is. You put a piezometer out there, you have to instrument it for 3 months to find out where it is. Take you forever, the potentiometer. Cone pen is great on seeing the zone of saturation. Well, that tells you the whole story right there. There it is. Bottom of the pier, which is his anchored zone, got wet and lifted. Ooch, ouch. Simple shear deformation, the backside of the house, where he's 8 feet away from the pool and parallel to the pool. There you go. Oh, okay, Mr. Smart Engineer, how do you fix it? How did I fix that? I didn't do it by drainage. You don't drain clay. don't move women fast if you're making love to them, and you don't drain clay. Okay? So I want to get some pearls of wisdom down on you. Okay? You don't drain. Clay doesn't give up its moisture. IRS doesn't give up their money. Okay? So what do? What would you do? You dry pack the mud sill. You jack this up, dry pack, jack that up, dry pack, bring it all back up level. I haven't heard from him since 1984. As far as I know, he's doing fine. I did tell him, if you drain the pool, Smiley, for more than about 6 or 12 weeks, this ain't going to work, because that side of the house is going to settle. And we added that as a restrictive covenant onto his deed. Haven't heard. I'm sure he's retired and moved on, but we haven't heard from Case. Now, what are other things you can do? Today, you have limitless things you can do with geotextiles and geomembranes. Boy, back when I started practicing, we didn't have this stuff. We had gravel. That was it. Gravel's a pain in the butt to use for anything. You know, how do you get 3 inches of gravel under something? Well, you can't. And so now, you can actually put all kinds of geotextiles, geomembranes in underneath the pool and put a drain in, so that when the pool weeps this water, you're not causing as much. You're not having as much free water here to feed into the expansive soils. And when I started doing that and building these as reinforced shells with the uplift forces on them, I haven't had any problem. But I do have to issue that warning to them that if you drain the pool in less than 7 days. 7 days? Yeah, that's right. You drain it in less than 7 days. You shouldn't be taking this thing down more than 1 foot every 24 hours. Because it'll pop it right out of the ground from uplift. Now, you help that by having this drain here. If you have good subdrainage under it, you probably could drain it in 1 day. But you got to watch that out. You want to cover your butt on that one. So, but geomembranes, what do? We would use an Enca mat with a filter on either side. So we have a filter against the soil. We have the subdrainage. Then we have a filter on this side. We shoot the gunite right against the filter. And boom, you have full subdrainage. The only thing you got to remember to do is have the outlet line. You got to have a gravity drain. You don't want to have a sump if you can avoid it. Sumps always go off in the bad weather when the electricity goes off. So you have to have a gravity drain. You can do that with a hydro-auger, with a horizontal drill. It's not that hard to do. All right, I'm going to stop there today. Start working on Chapter 5. And next week we're going to start doing writing assignments.